Now that we understand what a preference schedule is and hopefully have some idea of how to construct a preference schedule, we're going to change gears and talk about how to determine the number of distinct ballots that are possible when there are any number of given candidates. So you may wonder why these two are connected, but keep in mind that each column in a preference schedule represents a distinct ballot, and therefore the number of possible distinct ballots gives us the number of possible columns in our preference schedule. Now, keep in mind that we won't always have that many columns because there's no guarantee that every possible ranking will be represented, but there's always a possibility for that many columns within our preference schedule. So let's say that we have 3 candidates and we want to know how many distinct ballots are possible with these 3 candidates. So let's call them candidates A, B, and C. And let's look at the different ways that we can arrange those 3 candidates. So we have A, B, C, we have ACB, BAC, BCA, CAB, and CBA, or a total of 6 distinct ballots or 6 distinct ways to arrange those candidates. So you'll notice that the correlation here is that we take the number of candidates and multiply by 2, and that gives us the number of distinct ballots. So the question becomes, is that always going to work? Well, let's consider if we have 4 candidates. In that case, we can have ABCD, ABDC, ACBD, ACDB, ADBC, and ADCB. And that's just for possibilities starting with A. We also can have 6 different ways or possibilities starting with B, 6 different ways to write it with C, and 6 different ways to arrange them starting with D. So it turns out that for 4 candidates, there are actually 24 different ways to rank the candidates, or 24 distinct ballots. So as you can see, our method of multiplying by 2 kind of goes out the window with this one. So the question becomes, is there a way to be able to calculate the number of distinct ballots without actually having to list them all? And the answer is yes. So the long method that we have, which is impractical for a large n value or a large number of candidates, is to list them all out. That's what we did in our previous examples. But a shorter method would be to multiply the number of candidates available for each rank. So if we take the example of 6 candidates, the first choice, we have 6 candidates. So we can choose any of these 6 candidates for our first choice. However, once we make that first choice, now we're left with only 5 possible candidates because we've already chosen one of the 6. So our second choice, we only have 5 candidates to choose from. Then by the time we get to our third choice, we have only 4, and then so forth and so on. So the easy way to find the distinct ballots for n candidates is to multiply the number of choices together. So in this case, for 6 candidates, it would be 6 times 5 times 4 times 3 times 2 times 1, or 720 distinct ballots. So how many distinct ballots are possible for 10 choices? Well, to determine the number of distinct ballots for n candidates, we use n factorial. So the exclamation point stands for factorial. And factorial simply means multiplying consecutively decreasing whole numbers. So n factorial would be n times n minus 1 times n minus 2, so forth and so on. So for 10 choices and candidates, the distinct ballots would be 10 factorial, or 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or 3,628,800 distinct ways to rank those 10 candidates. So it's easy to see with 10 candidates why you would not want to use this process of listing all the possibilities in order to determine the number of distinct ballots possible. So in general, a preference schedule for n candidates will have at most n factorial columns. So if you have 3 candidates, it would be 3 factorial. If you have 8 candidates, it would be 8 factorial. And again, remember, that's the maximum number of columns. It doesn't mean that you will have that many columns because not every distinct ranking will be represented in all cases. So it turns out that like our distinct rankings, a factorial can be used to determine the number of ways you can arrange any n objects. So it doesn't just have to apply to our voting theory and this concept of finding distinct rankings or distinct ballots. You can use it in any scenario where you're trying to determine how many different ways you can arrange n objects. For example, if I asked you how many different ways you could hang 6 paintings in a row, well, 6 would be the number of candidates or the number of objects in this case. So 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1 would give us 720 different ways that you could arrange those 6 paintings. If we wanted to determine how many different words, and by words I mean just a string of letters, it doesn't have to be an actual word in the English language, could be made using the letters in the word house. Well, there's 1, 2, 3, 4, 5 letters in the word house. So 5 factorial, or 5 times 4 times 3 times 2 times 1 gives us 120 different words, or 120 different ways to arrange those 5 letters. And how many different 7-digit combinations can be created using each digit from 1 to 7 only once? Well, how many digits are we working with? 7, so 7 factorial gives us the number of combinations, and that's 5,040 in this case. So let's look at the Wildcat softball example. The members of the Wildcat State University softball team are holding an election to choose a senior captain. The 5 candidates are Alice, Beth, Kara, Dawn, and Eileen, and the results of the election are shown in the following preference schedule. The first thing that we want to determine is how many distinct ballots or columns on the preference schedule are possible with this number of candidates. So we have 1, 2, 3, 4, 5 candidates. So 5 factorial, or 120 distinct ballots. Now, to recap what we were talking about earlier with the preference schedule, let's go ahead with the Wildcat softball example and answer a few additional questions. So how many members voted? Well, remember that each column tells us at the top how many people voted that way. So we have 8 plus 6 plus 5 plus 4 plus 3 plus 2, or 28 voters in this election. Oh, I went a little too far, didn't I? Next, we want to know how many second place votes did Eileen receive? Well, we go to second place, and we see that Eileen received 6 votes here, and 4 second place votes here, or a total of 10 second place votes. And who has the most last place votes? We go to last place, or 5th in this case. We see that E has 8 votes. C has 6 plus 5, or 11 total votes. A has 4 plus 3, or 7 total last place votes. And B has 2, so C has the most last place votes with 11.